when we say that we have scientific methods, we mean there's a whole set of tools that we can use to understand things scientifically. And it's not a cookbook, cookie cutter, first we do this and then we do this. It's partly a way of viewing the world. And it's a way of viewing the world with good observational skills, a whole lot of curiosity, and a healthy dose of skepticism. I mean, if I really had to describe 3 tenets of viewing the world scientifically, that's them. Good observation skills, sense of curiosity, and a healthy dose of skepticism. You know, never taking it for granted. Noticing things so that you can then say, huh, that's weird. We'll talk about it after 4 minutes. It's not a recipe. Now, at the base of studying something scientifically, there are always observations. There are always observations. But there are observations through the whole process. So, you know, when we say observe, ask a question, well, yeah, but the observations happen throughout. So we have to be aware enough of phenomena that are occurring that we can ask questions about them. And it's been said that, you know, some high percentage, 90% of all scientific discoveries start with the words, huh, that's weird. In order to be able to say, huh, that's weird, you have to have observed enough to recognize patterns and to recognize when something doesn't seem to fit with a pattern. And you guys all did a great job with pattern recognition. The very first week, we had the cubes out, and you were making predictions about what was on the bottom. You have to ask questions about what's going on, and then once you've got some questions formulated, you collect more data that relates to that question. The formation of a hypothesis. I think I said this before, I will say it again. It's not an educated guess. A hypothesis is a working explanation. It's the best explanation that we have thus far for how something works. Can there be competing hypotheses? Yes, there often are. So the moving rocks in Death Valley, there were multiple hypotheses over the years. They weren't sure what was correct, and people were adherents of one school of thought or another. There can be multiple competing hypotheses. You can have 2 hypotheses, neither of which have really, you know, both of which have some evidence to support them. Once you have a hypothesis, though, you have to go the next step with it, which is to test it. Having a working explanation allows you to make predictions and test them. Well, if it works this way, then when this happens, we should see this. That's that testing piece. And in some types of science, it's very formal experimentation. In others, especially in biological science, it's a lot of data gathering observationally, you know, like field biology. You don't set up experiments in field biology, you just gather data. In a physics lab, they do actual experimentation. It's not just data, it's experimentation. There was one a number of years ago, so I told you about the salt mines under Lake Erie and the big salt crystals. I don't know if it was the Morton mine at Geneva or if it was another one, because there were multiples. There was a large, basically a backyard above-ground swimming pool full of dry cleaning fluid, parked in a dead-end tunnel for a decade, courtesy of a physics department at, you know, I don't know, MIT and in cooperation with Cornell and somebody else. Because there are subatomic particles that are unaccounted for. We'll talk a little bit about subatomic particles. We don't go into them in depth. But you know that there's the proton, electron, neutron. Well, below that, you've got, let's see, quarks and bosons and leptons and Higgs bosons and all these other weird little particles. And neutrinos are something that partially makes up a neutron. It was hypothesized that neutrinos from space, when they hit the planet, go right straight through. Just plow through you, plow through me, plow through layers of granite. And so particle physicists said, well, if that's the case, then we should be able to, we need to find a place where we can observe them where we don't have all these other factors and where we have some material that they could travel through and they would leave traces. And basically, I don't remember why it worked chemically, but dry cleaning fluid ended up being that material. And a salt mine 2 miles down under Lake Erie is great because you don't have all sorts of other things going on. There are all sorts of other forms of energy that you know can't penetrate that far. Radio waves and ultraviolet from the sun and all these other forms of energy. So they parked these swimming pools full of dry cleaning fluid in these tunnels under Lake Erie for years and collected data because they said, okay, well, we believe that this is what's happening. If that's happening, we should see evidence of them here. So you form a hypothesis, you make predictions, you experiment. How many of you had Mrs. Haylett for science? Okay, so you should all nail this one. If not, don't worry, I'll disabuse you of any other notions. So you do an experiment. Do you ever prove your hypothesis? Do you prove your hypothesis? If you answer this wrong, I will go get Mrs. Haylett. I'll personally have her come over here and glare at you, if you had her. Do you prove a hypothesis in an experiment? Can you prove a hypothesis in an experiment? You never prove a hypothesis. We don't prove anything in science. Science has never proved a single thing. Next time somebody tells you, well, it's scientifically proven. No, it's not. We don't prove stuff in science. We disprove. That's all we're working at. That's all we're doing is picking away at what we think we know. Picking. Chipping away with little tiny rock hammers on giant granite faces. You have a hypothesis. You make a prediction. You test it. Your results either support the hypothesis or they don't support it. If they support it, is your hypothesis proven? Nope. But it hasn't been disproven yet. And one of the fabulous examples of this, years ago, there's a guy named Brian Greene. He's a physicist. He was at Columbia University in New York, and he works on string theory, which is, so far above my pay grade, it's not even funny. It's crazy, weird physics. And subatomic, little tiny strings and vibrating membranes, and this is what makes up the universe, etc. 11 dimensions, and they're coiled up inside one another, and woo! So he came to speak at YSU. This was, 2008. Fantastic. And he said, and it's really stuck with me, I go to work every day, I work on string theory. This is what I do. I go to work every day trying to break my own theory. I mean, he didn't come up with the theory, but he's one of the big proponents of string theory. He's one of the leading voices on string theory. And he said, I go to work every day and I try to break it. Every single day I go to work and I try to disprove this thing that I've been working on for the last 25 years. And we could do it one day. We could make it all fall apart. I don't know what I'd do then. But that's what science does. You try to disprove. Because if you try hard enough to disprove it and you can't, that's pretty solid. That's the point at which a hypothesis that has been tested repeatedly by one single, one single hypothesis that has been tested repeatedly by numerous people, thousands upon thousands of scientists and teams and everything else, and has yet to be disproven. That's where we start to go, there might be something to that.
Staff, please excuse interruption.
Scientists. Okay, so if we have a hypothesis that has been repeatedly tested by lots and lots of people and nobody's disproven it, then there might be something to it. So, one scientist cannot make a theory. So if you have a hypothesis and you support your own hypothesis and you can't disprove it, it doesn't make it a theory. That's important to understand. Okay, so that's all we're going to say about scientific methods. It's more than one method. It's a way of looking at the world, and those steps lead back and forth and into one another. Now we're going to start with the math. Okay, scientific notation, you all know how to do it. You all know the basics. You've probably been doing this since middle school. You do it in math regularly. And I would say, out of all my historical data of having taught chemistry for X number of years, 100% of you are comfortable with making this number into this number. And 100% of you are comfortable making this number into this number. Good. Now we're going to talk about where my observational evidence over the last X number of years of teaching chemistry tells me you might trip over your own feet. Okay? Because I know where people make mistakes because I've watched them do them enough times. So now we're going to talk about where you're likely to screw this up so that you don't have to screw it up. So that you learn how to walk around the hole in the sidewalk and not step into it. First of all, just a quick review. You all know that a number in scientific notation has to only have one digit in front of the decimal, and that digit obviously has to be between 1 and 9. You can't have 10 is not a digit, 12 is not a digit, that's 2 digits. So you have to have a single digit here. That value has to be between 1 and 9. You can't have a 0 there. And then you can have anything that you need to back here, okay? Or back here, I should say. That can be as many numbers as are appropriate. You don't know what's appropriate yet because we'll start talking about sig figs next week, but you can have as many numbers there as you need to. Okay, you could have 2.9973297 times 10 to the 8th. Okay, there's no rule about how many numbers can be there. It's as many as are appropriate. And we'll, like I said, we'll cover what's appropriate next week. You're all comfortable with that. You all know that the negative power of 10 means you're dealing with a number smaller than 1. You get that. Now, as it relates to this, the place where I see people run into trouble is moving those decimals around when you're already in scientific notation. This typically happens as a result of doing an operation with two numbers in scientific notation, and let's say the answer you get is 42 times 10 to the 7th. Okay? So that's not in proper scientific notation. If you give me that on a test or quiz, it's wrong. So it has to be 4.2, and some of you can do this in your head already right off the bat. You never miss it, and you never get it wrong. I'll tell you what, you're smarter than me. Because I wrap myself around my own axle doing these, which is why I have developed what I call my P-brain methodology for not tripping over your own feet when these get complicated. If you're getting them all and you're never missing them, and you're not screwing yourself up and missing points, then you don't have to employ my P-brain methodology. But if you find that you're making those mistakes, I would advise you to use Moser's patented, it's not really patented, P-brain technology for not screwing up moving these things around. So we'll deal with 4 potential cases for moving things around. So we've got here 42 times 10 to the 7th, that needs to be 4.2. All right, what I do is I actually fluff that number all the way out. And it looks like a kindergartner did it. I don't care. I'd rather do that than screw it up, because when I try not to look like a kindergartner, I screw it up. Oh well. So I literally go 1, 2, 3, 4, 5, 6, 7. Okay, that's the entire number. Now to move my decimal, I'm going to go backwards, and I go under one way and on top the next. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 4.2 times 10 to the 8th. Now here's what I find. Every single one of you, if I woke you out of a dead sleep at 2 in the morning and made you answer this with no coffee, could tell me that in this number, the decimal needs to move 1. And every single one of you could tell me that that means that that number is going to be different by 1. Where it's not usually intuitive, and for some of you it is, bless your hearts, is whether that's going to be a 6 or an 8. That's where people screw it up. That's where I screw it up. Now, this is the easiest of the 4 cases that we're going to do. The power, the exponent is positive, and this number is a whole number. It's not less than 1. These are the easiest of the 4 cases that we do in my mind. Even I can usually do this one without drawing all my bumps. Once you get warmed up, these get pretty easy. Let's do the more difficult of the cases. So this is something that you might get as a result of doing an operation with 2 numbers that are in scientific notation. Okay? So the thing that's the same here, the exponent is still positive. We're working with a positive exponent. What's different here is that the number we got as a result of our operation is less than 1. Okay? This is a fractional number. So we know that this needs to be 4.2 times 10 to the something. Okay? And again, what I do is I fluff the number out, and I call it fluffing the number out. You flush it out. You put all the zeros in. So I'm going to recopy this. And I'm not even sure how many zeros it is. I'll add extra. It doesn't matter. 1, 2, 3, 4, 5, 6, 7. Okay. So that's the number I'm actually dealing with. And if I wanted to write that off to the side just for my own purposes, that's the number I'm really dealing with once I flesh it out. To go back and put the decimal where it belongs, I go 1, 2, 3, 4. So this is 4.2 times 10 to the 4th. Now again, I am fairly confident that 100% of you could tell me that decimal needs to move 3 places. This exponent is going to be 3 different. Where it gets confusing for some people, including my pea-brained little old self, is that exponent going to be 10 or 4? You know? So this is the second, so if the first one was the very easiest, this is the second easiest. This is not too hard. When you've got a positive exponent for some reason, some sort of psychological trick, students are typically more comfortable with the positive exponents. So let's get to the third case, which is where it's a little bit dicier. It's still not the hardest one. The weirdest, hardest one is the one that even in the other class video went, well, wait a minute, no. Yep, that's the way it works. So let's do the third case. Okay, so we got this as a result of some operation that we did, and the answer we got was 420 times 10 to the negative 6th. I mean, you would never write that number. You all know better. You know it has to be 4 point something. But you can end up with this as the result of doing a math operation. So, once again, we're going to flesh it out. Now, if this x and the negative exponents just freak people out. I don't know why, but they do. If the exponent is negative, the number is less than 1. So to flesh it out, I know this is, you know this, you could do this in your sleep at 2 in the morning, but I'm putting all of my extra zeros out in front, because if the exponent's negative, the number's less than 1. And to flesh it out, I just go 1, 2, 3, 4, 5, 6. And I didn't know how many zeros I needed. I just threw a bunch out there and I'll land where I land. Then, to get this back to a 4.2 times 10 to the something, I just go 1, 2, 3, 4. So this is 4.2 times 10 to the what? Negative 4th. Okay? And it's negative 4th because this is a number smaller than 0, or smaller than 1, not smaller than 0. Smaller than 1. Okay, it's a fractional number. That's, I would say that that's typically the third hardest. Let's look at the fourth. Okay, so here I've got the two things that tend to confuse people piled up together. And again, this is not a number you would ever write. You're smarter than that. You wouldn't write this. But you might get this as a result of an operation with scientific notation. So we've got a number less than 0 here, and we've got a negative exponent. And those are the two things people hate the most. So again, we flesh out the whole number. Now I'm just putting a bunch of zeros. Whoops. Okay. 1, 2, 3, 4, 5, 6, 7. I didn't put enough zeros. 8. And then we want to go all the way back to here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 4.2 times 10 to the negative 12th. Okay. It's not hard. It's not difficult, but historically I've seen that people get confused about it. So let's now look at where you're going to apply this. We're going to actually use this in context. We will do one quick practice. We don't use as much addition and subtraction in chemistry. We use tons of multiplication and division. We use the multiplication and division all the time, and you will start using it in context on Monday when we start conversions. So let's practice we'll practice an addition problem, and then we'll kind of move on to the stuff we use a lot more. The exponents have to match. So if we have 5.6 times 10 to the first plus 3.2 times 10 to the second, we can't add those things together as it is. We can't add the 5.6 and the 3.2. And what you know intuitively is because we're talking about 56 and 320. If we add the 5.6 and the 3.2, we're adding tens to hundreds. We can't do that. So we just have to make the powers match, have to make the exponents match. Doesn't matter which one you move. I typically choose to move the one that's going to give me an easier value to work with. So I'm going to do 5.6 times 10 to the first plus 32 times 10 to the first. And when it's down to powers of 1 and 2, even my pea-brain little self can do it without making bumps. So you probably can too. So all we have to do at this point is take these leading numbers, add them together, and the exponents don't change. We don't have to do anything with the exponents. So our answer here would be what? 37.6 times 10 to the first. Okay. Let me move this up a little bit. And if we put that into correct scientific notation, we know that we have 3.76 times 10 to the second. We're talking about 376 here. Those are pretty easy. They're not terribly difficult. And typically the things you're adding are only 1 or 2 orders of magnitude off. So those exponents aren't going to be all that different. You're not taking something to the negative 19th plus something to the 27th, because you really just can't do that. You can, but it's stupid. So those are pretty easy. Now let's look at the multiplication and division, because we use these all the time. Okay, so we have a multiplication problem here. And what's glorious about this, we don't have to move any decimals. We are just going to add the exponents. So we take this and multiply by that. 5.6 times 1.2. And then it's the whole mess times 10 to the 3 plus 7. Couldn't be easier. Couldn't be easier. So we get 6.72 times 10 to the 10th. Very easy. Now, of course, you could end up with something here that was not in correct form, and we'd have to do that decimal movement. And you know that happens. It just does. Now let's do a division problem, then I'll turn you loose to work on practice problems. If we have 5.6 times 10 to the 4th divided by 1.2 times 10 to the 9th. This is easy breezy. It's fantastic. Again, we take these front parts, we divide them, 5.6 divided by 1.2, make the whole mess times 10 to the 4, and because we're dividing, we subtract, minus 9. Okay, so we get 4.666, and it's repeating, times 10 to the negative 5th. It's not hard. Of course, you can end up, and often do end up with a number where you have to shift the decimal around. And that's, use my pea-brain methodology, you'll be fine. Homework is assigned. You practice some problems. Tomorrow we FIP. And assuming that everybody is moderately successful with the FIP, we move on to using these in